All right. Hello and welcome, everybody. It looks it's about time to start this session. I forgot at which time it is in the real venue. It's 5 o'clock in my time zone, and I guess we have various other time zones present here. I see a few people still dropping in and dropping out. Anyway, hello and welcome to C++20 and the more specific topic, templates, and here we talk about concepts. First things first, it's really great, at least in my opinion, that we can have this conference that way, that John and all the others went down and practically make two conferences happen at the same time. So one in the real venue and the other one here virtually, and they're combining them. I think that's incredible. Also, all the volunteers who help running both conferences at the same time. So let's give them, even if a lot of them cannot hear it, give them a warm hand of applause, okay? Because I think it's really incredible what they are doing. Because we are here in the virtual part, this session will be recorded, I think, as all others. You're in webinar mode. That means that by default, you can speak, but nobody will hear you. We can enable speaking rights for you. If we do so, please note that your audio voice will be recorded. I will allow this option at the end of the talk. I hope we have a couple of minutes left there. If you like to ask questions, then please use the Q&A. Ask your question there such that other people can upvote it. And I will look from time to time to the Q&A and see what's going on there and answer a couple of questions. I'm not really able to follow the chat during my presentation, so you feel free to chat, but if you have questions to me, then use the Q&A. You can also reach me on Discord later, preferably, possibly tomorrow, because I have to leave soon after the talk. But yeah, feel free to grab me via Discord, email, or now in the session or at the end of the session. Okay. So my name is Andreas Fertig. I work as a trainer and consultant for C++. I'm part of the standards committee. I'm the author of C++ Insights, a tool to help to look behind the scenes, which we will not use that much today, or not at all, I think. And I'm about to finish my new C++20 book called Programming with C++20. So if you have appetite for that, then check it out. Also, if you want to learn more about C++20 in general, I offer next week a class at CppCon 3 days about C++20. And I think it's still time to sign up. So, but now let's start with C++20, right? And C++ and templates. Now, let's first talk about another language. I'm German. My last name is a very German word. It's Fertig. You can translate it into finished, ready, complete, or completed in English. It's a really nice one. And if you form a sentence in German with it, then one sentence, for example, can be, Ich bin fertig. And that translates to, I am finished. Depending on how I'm saying that and my facial expressions to it and my mood, which you may know at the point when I'm talking to you, then it can also mean, oh, I'm totally exhausted. So two different meanings for one and the same sentence. Doesn't that sound like C++, right? We can do things multiple ways. So let's talk about concepts. They're so great. With concepts, we can formulate requirements for type the first time in a proper way. If you really want, you can compare it to a std enable if. But it's such a teeny tiny portion out of what std enable if can do. Concepts can do so much more, so it's an unfair comparison, and it's just a teeny tiny part of concepts, but you can compare it if you like. So concepts consist of the definition of a concept, which we got a new keyword for called concepts, and requirements. Can add requirements to a concept, and we have a new keyword for formulating them. That's requires. Because concepts are only interesting or needed in generic code, there are always templates. The figure here at the middle of the slide illustrates this. So they always start with a template head, like we know it from function templates or from class templates. And in there, we can have one or several type names or classes, type and non-type parameters as we want. And then in the second line, of course, it's C++, you can also put it on the same line. There's the keyword concept. So this tells the compiler and to us that we start a concept definition. And then there's the name of the concept. Of course, we want to name that thing. So I picked a really bright one, my concept, that's unique, I think, worldwide. And then I'm assigning the requirements to that concept. And the first statement you're seeing here stood same as, that's a concept from C++ 20. The rough rule of thumb is if it starts with is, underline, or underscore, then it's a type trait. If the is omitted, then it's a concept. And what you can further see here is that we can chain the requirements together. So we can say that same as is one of the requirements, and then we use Boolean logic to concatenate it with is class V or is enum V. Okay, so first with an and then with an or. So this is how a concept in principle gets built. So let's look at what we can do with all that new power. My motivating example for today is the following. Suppose I have a function called add, and its job is to add all the values together that are passed to it as parameters. Can be of a class type, can be an integer. What I'm showing here are only integers, and what you can also see is that add should take an arbitrary amount of values of object of types, which, guess what, makes it a variadic template at the end, right? So I'm happy with the first two lines, 1 and 2, x and epsilon, they're fine, but I'm unhappy with line number 3. Why? Because there I'm mixing integers 2 and 3 with a double, 3.14. I don't like implicit conversions here. I don't like mixed types. So this add function starts coming with 2 requirements. One is it should take an arbitrary amount of parameters, and the second one is it must ensure that all of these parameters are of the same type. Okay? Sounds like a pretty straightforward thing. Let's see what we can do in C++ 17. Various solutions are possible. This is the one I'm going with for today. The grayed out part isn't majorly interesting for this solution. I walk quickly through it. So first in line number 2, I'm creating a variable template called rSameV. It uses the conjunction V from C++ 17 together with .sSame. And it compares all the parameters in the parameter pack TS with the first parameter passed to this variable template T, whether they are of the same type. So if I pass in a parameter pack, the first parameter will be split up, and it will be compared to all the parameters in the parameter pack. And the rSame and the conjunction, which ends them together, ensures that all types in this parameter pack are of the one of the first parameter. So by that, rSame ensures that every parameter in this parameter pack is the same. And then the second helper in line number 4 to 10, it's called first argt. And its job is to pass a parameter pack and get out the first type in this parameter pack. Okay. With that, we have an option to compare all parameters in the parameter pack and to get a type out of the first parameter in this pack. And because all are of the same type, it doesn't matter which one I grab. So the first one is a good choice. And then the not so grayed out part below, that's the actual implementation. In line number 1, we can see it's a variadic template because we have the type name ... there. In line number 3, then I see, okay, the function's name is add, and it takes all the parameters here in. And in line number 5, we can see I used C++17's fold expressions to apply the add operation to all the arguments in the parameter pack. Okay, I think that's okay so far. But then there is this line number 2, which I briefly, I really didn't talk about it, right? So it's the std enable if t. By that we can say it's the state of the art enable if, because it's enable if t, so it already gives me back a type. First argument is the Boolean condition, and the second, the type that my enable if returns if the Boolean condition is true. I suppose a lot of you already know this, and some don't, and some forgot. And then, oh yeah, this enable if, that brings me the return type, right? Because the first argt, if my r same way is true, then the enable if passes the first argt, so the first type from the parameter pack, as my return type, because there is no other return type. I think it's the best way where to put an enable if, because nobody else can tamper with it. But for readability, for understanding, for teaching, it's quite hard, not to say a nightmare. Some of us, are used to it. Some others are don't, and I all the time understand those who say, "Oh, so many anchor brackets. Sorry, you lost me there." Okay, I totally get that, and it's not obvious what this enable if does. It gives me the return type, but it disables something. Oh yeah, if the return type isn't there, then we cannot instantiate this function. Sure, all right, not a point to know and to teach. This is what C++20 looks like. I still need the helper R same way. And in line number 1, I still have a variadic template. But line number 4, look at that. It's a normal variadic function now, right? It says auto. There's the return type. I was missing that before. And then add takes the parameters from the parameter pack. And line number 6 is unchanged. It's the fold expression from before. So line number 4 alone, I think, is an improvement because I have a normal function declaration at this point. But what really excels here is line number 3, because line number 3 now spells requires R same. Requires, because that's what enable if did before. It was a requirement, but it was spelled enable if. Well, so requires. It's now clear that this is a requirement. You may have to look up what RSameWe is and does, but you already know this is a requirement for this function. And if this requirement isn't satisfied, we cannot instantiate this function template, okay? That's, I think, way easier to teach than the other thing we saw before in C++17. I really, really like this already. That's a win. So let's look what concepts, where concepts can be applied. These are the various application areas. In the template head, we have our first concept, C1. That's called the type constraint. We can use this instead of type name or class to upfront specify constraints or requirements for this type. So we no longer have to say, well, yeah, give me a type, and later in some static assert in the function body, we say, oh no, that was the wrong type. Not that one, please. So we can express this here, and the major benefit is this is documentation. Okay, I directly see that. I don't have to go down to the function body to read 100 lines of code to figure out that there's a static assert that says no to that type. It's in the type constraint in the template head. The next one, C2, we already saw. That's called the requires clause. That's what we used in our add example. Okay, we can use concepts here or type traits. The requirement is it has to yield a Boolean value, so true or false. And then C3 and C4 are called constraint placeholder types. That's always the case when we put a concept in front of auto. So it can be an auto variable or a auto return type here, or a auto parameter. C4 is slightly new. Before, we only had this option for generic lambdas in C++40. They could have auto parameters, but now we can use them in all functions. Then they are called abbreviated function templates, and I will show you an example later. And because it's auto, we can put a concept to constrain it in front of it. And then at the end, we have our trailing requires clause with C5. Same as for the requires clause, we can use concepts or templates at this point. Okay, so these are the application areas for concepts where you can place them. Now going back to my add example, and if we think a little bit more about requirements and what all that means, then we can say currently add only prevents mixed types. And of course, it allows multiple values. So this was one requirement. But there are more, and most of them are very, very implicit. So we can currently call add with only a single parameter, even with 0. And that makes no sense, at least to me. In highly generic code, you can argue that it makes sense, but the name implies that we are adding things together. So calling that thing with 0 or only one argument doesn't make sense. So let's say we want to constrain that. Add must be called with more than one parameter. The other one is that whatever we use to add together must support the plus operation. That's a very implicit requirement made in the function body. It's a design decision at the time we write this function. Of course, plus is very sensible, but we could also have said that the object that gets passed in the type needs to provide a member function called add. We could also go crazy and can say it must support a member function called subtract. I would not advise you to do that, but it's possible. And in all the cases, it's not documented anywhere, but in the def down in the function body of the function template. So that's really bad. And that's the parts that give us these page-long error messages if we pass in a type that does not support this operation. And we have no good way to check that. Then the other thing is the plus operation probably should be no except, because the version of add I showed to you all the time was marked with no except. And if we pass in integers, then we don't expect an exception, right? And if we pass in another type and add is no except, well, then that type's operator probably should be no except as well. Maybe we want to create a different function to overload on it. And the next one is the return type of the plus operation should match the one of args, so the base type of args here, which is the case most of the times, but sometimes operator plus does return a different data type. And there may be good reasons for it, but let's say for our add function, we want to restrict that. The operator plus must be returning the same type as the type in the argument pack. Okay, so a lot of requirements, which brings us to the requires expression. There is a lot of requires going on when we talk about concepts. I always read such a requires expression like a function. The function's name is always requires. Maybe it's like a constructor because it doesn't have a return type. And after the name, we have the optional parameter list. That one can be empty, or we can put parameters in. Which parameters? All types that are available the moment this requires expression gets evaluated. These are built-in types like int, jar, types you pulled in with your headers like std_string, or types that are coming from the concept or from the template where this requires expression is used in. So t and u, for example. And then this is only used at compile time, okay? It will never hit your binary. So we can say here t, we can say tref, we can say t star, we can go all crazy with left const and west const at this point. So it's like a function definition, which is never executed in real code, but we will see how handy it is that we have this opportunity at this point. And then we have the body of the requires expression, which funnily comes with one requirement, and that is that it must have at least one or multiple requirements. Makes somehow sense. So the requires clause we previously saw in the concepts C3 and C5 on the slide where I showed the concepts overview, that's a Boolean expression. While a requires expression, as we have it here, is something more complicated. And we know these things already from noExcept, because for noExcept, we can mark a function as noExcept, but we can also query whether a function is noExcept or not, okay? And in general, or as a rule of thumb, we can say that our requires clause is like an if that evaluates a Boolean expression, and a requires expression returns such a Boolean value. Okay, that's how the two fit together. Now, a requires expression can have requirements, and there are 4 different requirements such a requires expression can have. A simple requirement, a nested requirement, a compound requirement, and a type requirement. Okay. We will only look at the first 3 regarding the add example. I will show a better application area for the type requirement later. I shortened all requirements with 2 letters to have them show up in source code, which I'm now going to show. So let's start simple, right? Simple things first. Simple requirement. A simple requirement checks only whether an expression is valid and will compile. That's the job of a simple requirement. And for my example, it's small, it has to fit in a talk and on the slides. In reality, it's better because here in line number 3, what I have to do is I have to repeat my fold expression. This is something I really, really don't like, but in real code, it's better. So what a compiler does here is it tries to instantiate this fold expression, sees if that would work for the provided data types. So practically it checks whether there's a plus operation, and if so, this requirement is met. If not, the entire requires expression returns false. Below you see in code what that means. If I now create a struct, call it noAdd, and call add with 2 instances of noAdd, that will now no longer compile our requires expression restricts that. Okay. Remember to ask questions in the Q&A. Feel free to do so if you have any. So going on from the simple requirement to the nested requirement, which is also a little bit nasty or dangerous. In line number 4 and 5, we see a nested requirement. A nested requirement always starts with requires. Remember that I told you that we have multiple places where we use requires? All right, so that's another one. And it's important to have this requires here, because if we are taking line number 5 as an example, without the requires, what we have left is the size of ... args greater than 0. And without the requires, this is a simple requirement. So all the compiler will do is trying to instantiate that. And because we are passing in a parameter pack, that operation will always succeed. Whether there are 0 arguments in the pack or not, it will succeed. So we need the requires in front of it to force the compiler to not only instantiate it, but also to evaluate it, to get the value greater than 1, true or false. And if you forget this, then it behaves differently. So this is a small trap you can run in with nested requirements. With the two nested requirements we have here, we can check off our requirements or requirements to the function add A, B, and C. Because now, as the code below illustrates, I can no longer call add with mixed types, so to and no add will not work, and I can no longer call it with simply to. Okay, that's great. And I would say it wasn't that complicated. Now, there are two things missing, two requirements, which brings us to a compound requirement. A compound requirement can do two things. And these are the two things we are currently missing. And you can them in 2 steps or in 1. The 2-step version is line number 8 and 9. I talk later about that. And the do it in 1-step solution is line number 10, which I prefer for keeping my code clean and keep the repetitions down. Because as you can see, line number 10 starts, well, with my fold expression once more. But as I said, it's probably the example at this point. So my compound requirement starts with a compound statement at this point, so curly braces, and then in there the fold expression. Now, after the curly brace, we see no except. That no except makes the compiler check whether this operation that was in the curly braces, so in our case the plus operation, whether this was no except. Okay, so that's the first check. And the second one is the one after the trailing return type like notation where it says same as. Same as is a concept which checks whether 2 types are the same. And I'm passing first argt here. And for all of those who listen carefully and probably fast enough, they also have to pick the angle brackets apart. They will now ask, well, you just told me same as takes 2 arguments, but you're passing only first argt, makes it 1. That's true. The other one comes from the compiler. The compiler injects the resulting type from our compound expression into the same as a first argument, making it 2 arguments. So this is a nice way of grabbing the return type or the resulting type of this entire plus operation and feed it into a concept. Okay, this is the 2-in-1 version. We can also split it like in line number 8 and simply first check for no except, and in line number 9 then check whether the plus operation returns the same type as the first type in our pack. I prefer, as I said, for simplicity reasons, line number 10. And now we can see that all the other requirements are met as well. So A, B, C, D, and E, we can all check them. The sample code below illustrates they will not compile anymore. So excellent job. We formulated a requires expression restricting our add function. But how do we do this? So this thing now needs to get attached to our actual add function, right? And this is one way to do it. It's probably the fastest one. It's called an ad hoc constraint. And you can spot this whenever you see a requires. We have it here in line number 2. It starts with requires, and then the gray part, that's the requires expression we just built together. Okay, it's gray because it's not important anymore. And we plug this into our requires clause. So the first requires is the requires clause using the result from the requires expression we just built. And this is the requires. And whenever you see that, there is a high chance that this is a code smell. Why? Because we just spent 10 to 15 minutes to build these requirements, to build this requires expression. And now we are putting it in a single place. But what if we want to use it in multiple places? Please don't say copy and paste. That's a nil-value answer at this point. I'm not accepting that. So there may be good reasons for having that concept of this requires expression only in this place. Okay, for my specific add example here, you could argue it doesn't satisfy any other functions, requirements, and so forth. Then, okay, make it an ad hoc constraint. But usually you like to make it a concept. Okay, this is our actual first concept we create. The gray part is the requires expression we did build the entire time during this talk. And now in line number 2, I start my concept, giving it the name addable. It's introduced by the unique concept keyword, and it adds the requires expression to it or assigns it to it. And now I can use that one in line number 11 by saying requires addable. Okay, it's expressive. Once again, like with the enable if replacement, it now says requires addable. We might have to look up what addable exactly does, but it's now crystal clear that this is a requirement for this add function. And once we go through the requirements of addable, it becomes also clear what that thing checks for, or what the requirements of add is. And now I can use this concept in even more places. And I think that this version, even if we not reuse it, can be more pleasant for our eyes, because the function is now shorter and the concept is out of the function and it's not glued together like before. Okay, so this is how we define a concept with all the existing 4 different kinds of requirements. Since we spent an incredible amount of time building that one, because for the first time we could and it was worth it, there's something else that we should consider more than before, and that's testing our concepts. Okay, and doing that, my approach is I have a struct template, I call it stub, and it takes 3 non-type template parameters, no except operator plus valid return type. And inside it either provides an operator plus, which is or isn't no except and returns the right type, or it provides a different operator plus, which returns a different return type and is or isn't no except. So these switches allow me to configure my stub. And in line number 16 and 19, I'm creating nice handy names to these stubs using aliases, such that I don't have to remember what exactly stub true, false, true was again. No add. Now I know it. Okay, make it referable and easy to remember. And now the best part, I think, comes, and this is, we have our testing framework built into the compiler this time. Because concepts are compile time things, we can use a static assert together with our concept and feed it in different combinations and test it at compile time. So line number 2 says static assert not addable int and double. Yes, that will pass if it's prefixed with not. And the second one tests whether it can be used with only a single parameter or not. And then valid class, no add, no except, and so forth. They all check the different combinations. And these checks run all the time when you compile these unit wherever the concept is defined in. Okay, no extra testing framework needed. It's built in. It's brilliant, I think, and important. Remember that when you're creating concepts. Now, I told you we have also a new form of templates called abbreviated function templates. And here's a motivating example. This is supposed C++17 code. They have a function template called doLog. Internally in line number 4, it acquires a global mutex and assigns it to a log guard. And then in line number 6, it calls the function f, which is the parameter that got passed into the template or to the function. This is a pattern I like very much because it allows me to have this log only in one place and everybody let it simply call it. And if we once later like to change the global OS mutex variable here, then that's not a big issue. We don't have to touch everybody's code, just the single one. However, there are 2 things that I don't like that much about this approach here, or this code. That's the better phrasing. The first one is the template head. Okay, that's a really simple function template here. I mean, it's 7 lines of code, and you can also format it with less lines. Typing this entire one line number 1, that's really a burden. Okay, and it's long. It's as long as the function definition itself. But the even worse part is line number 6. I'm calling f. I told nobody that I will do that. Nobody knows that when they call do locked, they have to pass in a callable, a function, something that's invocable. It's hidden there. Sure, you say I can leave a comment. No, that's the wrong place for a comment. That's a thing that should be visible to everybody, that should be visible to the compiler as well, and that should be checked by the compiler. That's the wrong place for a comment. But we couldn't do better, easily at least, in C++ 17. Here's the C++ 20 version. First of all, 6 lines of code instead of 7 because the template head is gone. Line number 1 now has in the parameter list auto. This is a placeholder variable or placeholder type, and in this case, like with a generic lambda. Okay, and as I told you in the beginning, I can constrain these placeholder types, and in my case, I use .invocable, which is another concept from C++ 20, requires that the object or the type that gets passed in is invocable. The great thing is, this is documentation. It's not a comment, but it's documentation, and the compiler understands it, and it checks it, okay? That doesn't get wrong over time like a comment where nobody knows why that's still there. No, you will notice if you don't need it anymore or if you violate it, okay? So that's really brilliant. I like that. It's important to note or notice that all the time we see auto in a parameter list. That means that we are looking at a template, okay? I mean, the name gives it away, abbreviated function templates, but we may not see it later when we see auto. But auto is always a function template. It's true for generic lambdas, and it's true for abbreviated function templates. You can use C++ insights, for example, to peek behind the scenes, and then you will see that the compiler creates a function template out of that do locked for us. So it's a little bit syntactic sugar, but with the addition of the concept here, it's really, really helpful. Okay. So now we talked a lot about concepts, and I left something out that people most often want when they hear concepts. And that's better error messages. Because let's be honest, error messages of templates, they really, really suck, right? Page long, nobody knows where to go first, top, bottom, and what's in between, and what are all these types the compiler tells me about. So concepts should do better, right? But before we talk about error messages, let's have a look at the example I'm providing here. My example here is I have in C++ 17, say, a type trait that's called isContainer that checks whether a provided type or a given type meets the requirements of an STL container. And the requirements I make for that is it must have a value type, a size type, an allocator type, an iterator type, and a const iterator type. And in addition to that, it must have a size, a begin, a end, a cEnd, and a cBegin member function. Okay, 10 things in total, 5 each. That's the interface of a container in the STL, roughly. Now, it depends on how familiar you are with templates. Okay. Now, let's take a step back and say we like to look at this code with the eyes of our much younger us, depending on how old we are, but as the starter us. The first thing I see here is I have 2 times the name isContainer in line number 2 and 3. That's odd. Usually that leads to a compile error, right? But yeah, sure, Line number 2, that's the primary template, and line number 5 is the specialization. So no harm there. Yeah, okay, it will take some time until I understand this. I have. So that's sold. Very well. Then what is in line number 7, this stood void t thing doing again? Oh, you say practically nothing. Yeah, okay, the name gives that away. Well, okay. Oh, and line number 12 to 16, let's not talk about the repetition we have there, which is ugly as well, but what does this decal type thing do, and what was decal val again, and what? I can teach you that, but I rather do not, because it seems like a burden. It's unnecessary at that point. It obfuscates this entire thing. It makes it really tough for beginners to get into it. And then the next thing is, oh, line number 2, that is container thing there, that derives from std false type. I don't know what std false type is, but why the heck does line number 17, the other is container derived from a true type? Not that I know what true type is in the beginning. Oh, you say it's from the type traits header, and because it's a primary template and a specialization, it makes sense. And yeah, well, okay. It's not a usual object inheritance because they inherit from 2 different types. But yeah, okay. I'm buying that. Fine. And then below in line number 21 and 22, I'm testing my type trait. I'm creating a struct A, which obviously is not an STL container, and I ensure that it returns not with my isContainer check, and I ensure that it returns true if I use isContainer with a std vector of int. And then we spot this : value. Remind me again where this : value comes from. I do not see it here, and what it does. Oh, you say it's in the std true type and in the false type, and yeah, I see. Oh, you say I can create a variable template to get rid of this : value. So you're saying me I can write more code here to have less code there, which I then still do not really understand easily. That makes no sense. No, really. We learned to live with that for a long time, and I don't want to bash on C++17 or all the previous standards. It was great at the time, but it was still a burden. And as I said, I understand all the people who say, well, no, please don't show me template code. I don't understand it. Okay? That simply makes me cry. It makes me cry because it's so hard, and it has not to be that way. So here is what makes me much more happy. This is the C++20 version. Notably, first thing is only one name, container. I switched from isContainer to container because that was what the standard does as well. Is the type trait, without an is, it's the concept. And then I'm having a requires expression here, starting in line number 2, going down to line number 14. And there in it, in line number 4 to 8, this is a type requirement. It always starts with type name. And its job is to ensure that there is a type in T::. So in the namespace of T, there we check that there is a value type in it, there's a size type in it, and so forth, and that symbol is in a type. That's the purpose of this type requirement. Std T is gone, by the way, no longer needed. But the most beautiful thing, line number 9 to 13, because I have the option to add the parameter to my requires expression, I can now refer to it, and I can now say t.size. T.begin, T.end. That's normal code, okay? And once we understand we are in a requires expression, this is a check, this is a simple requirement. Compiler only checks whether this is valid for the given type. We are done. No decal type, no decal val. You can learn that if you really need it, but you don't have to anymore at this point. And line number 18 and 19, no : value, no true and false type. So much less to write, to read, and to learn. Isn't that great? Okay, and that's just for the eye, for the learning part. But I promised you error messages. So let's have a look at error messages. This is the code from the slide. This is the C++17 version. It's small because it's not that important. You already saw it on the slide. I added one more thing that's in line number 27. That's another static assert ensuring with if container whether std array of int of 5 is a container. And you see this line number 27 currently starts with a not. So it's not a container, obviously. The static assert says, once I remove this not, the static assert fires and tells me, oh, the static assert failed due to the requirement of is container. You might call me crazy, but I somehow guessed that because it's the only thing in this static assert. And now it fails and it tells me that it failed because of that. It prevents shipping that code to the customer. That's perfect, fine, right? But it doesn't help me to understand what the error is. So you might notice, you might not. Imagine you have a new large code base and you are stumbling into something. You have to check a lot of things. So let's see how C++20 does. Okay, here, same code, C++20 code. The requirement here, or the check here, line number 24 in this case, container of std array of type int. Is this true or not? Static assert was negated before I take away the not. Static assert fires, tells me that it's failed. Big surprise. And then tells me it's failed because of the container that wasn't satisfied, the requirement. That's not so important at this point because we only have one requirement in here or one concept, but it will be in a bigger expression. But the really important part here is the third line, the second node, where it says because type name t::: allocator would be invalid. And if I scroll up, you can see it at home probably, there's quizzling marks even under allocator type. Why? Because my std array doesn't allocate dynamic memory. It's one of the important things of a std array that it allocates its memory at compile time. Okay? That's a helpful error message. It's short, it's precise. It really tells me where to go down to, what to investigate. That makes me happy. That makes me smile. I can teach that stuff easily. And if you get it wrong, you get good help from the compiler assisting you in finding where the issue is. Okay, tremendously cool. Now, switching from concepts to other template improvements, let's have a look at non-type template parameters in C++20. We can now have floating point numbers, float and double, as NTTPs. And as line number 6 and 7 illustrate, I can now pass in +0.0 and -0.0. It never mattered for me so far whether 0 is positive or negative, but a lot of people are out there which really need to distinguish these two states. So in C++, we made this work. And there's one thing which I like to show you. It's once again in Compiler Explorer. And this time we are focusing on the assembly. So the code on the left, that's one from the slide, with a little bit more around it to make it compile. And on the right, we are now looking at the assembly. And there we can see in line number 4, this call to fun, which says then 0, 0, 0, a lot of zeros. And this line number 5 starts with a lot of F's and then zeros. And the first one is for the positive 0, and the second one is for the negative 1. If I enable demangling, which I just had turned off before, then we can see it, okay? They are the real values. And there's the reason why and how this works, because the number in hexadecimal notation is preserved. And that also means that our intermediate object files can get larger depending on the non-type template parameters we pass in, okay? It's no matter for your resulting binary because there you only have addresses, but for all the intermediate object files, they may now have longer function names to store, which to call and so forth. So that's worth to know, I guess. So that's non-type template parameters, the first. But we can do more. We can not only pass floating point types, but also classes and structs. So here I have a struct called fixed string. It's a template. It takes a char t and a size tn. And internally in line number 3, it creates then an array of type char t called data with the size n. And it comes with a const expr constructor in line number 5, taking a const reference of char t of size n, and it uses the copy n to copy all the data from that string that got passed to the constructor inside data. And now I can use it in line number 8, saying I'm creating a fixed string object, call it fs, and use uniform initialization to pass the string hello C++20 to it. That's cool, right? But yes, you got me there. Technically, no NTTPs are really happening here or nothing new. N would be an NTTP, but that was available all the time. So let's use that fixed string class. And this is now the new part. Line number 1, I can use my fixed string type as a non-type template parameter. I call it str. And I create another function struct, or another struct template called fixed string container. And it comes with a method print. And this print method couts str.data. So my non-type template parameters string effectively. And in line number 10, I'm now creating such a fixed string container. And now we can see for the first time, we can pass a C string in the angle brackets. Call that thing fc, and later in line number 11, I'm calling fc.print, printing out that string I created at compile time. That's nice, right? And we can do a bunch of more things at this point. So I guess that will be very interesting to see how it develops feature. Okay, C++20's non-type template parameters. Let's have another look at more template stuff. This time lambdas with a template head. Here's the motivation. I have this variable max, which is effectively a lambda because we assign a lambda to it. And its job is to figure out which of the two values, x or epsilon, is larger and return that one. And as we can see, it's a generic lambda from C++14 because of the order in the parameter list. I advise you to use the STL version, okay, that this is here for teaching purposes. Max in the STL is sufficient enough. And if I use this lambda here, max, I can call it like in line number 7 with 2,3. I'm happy with that. And I also can call it like in line number 8 with 2,3.0. And that's what I'm not happy about. It's once again mixing types, okay? I don't want that. And there was no real good solution I could recommend before C++17 before C++20 to make this work. It was always like, well, no, it's not code I'm showing you right now. Here's the C++20 version. In C++20, we can have lambdas with a template head. That means after the captures, we have in the angle brackets our template head. Okay, and in there we can put everything we can also put in for a function template. We can use type or non-type parameters. And this enables me now to say that my lambda max now takes a type name t, and I use this t for both parameters x and epsilon. Okay, the rest of the implementation is the same. And this effectively leads to line number 8 still compiles, but line number 9 now stops compiling because of the mixed types. Now we are in the template land, and there no implicit conversions are allowed, except if we really force them. But I don't here. So the compiler says, well, I cannot instantiate max because you're providing me with an int and with a double. I don't know what to do because your template only accepts one type. Okay, this is what I want. failing at compile time. It's really great. And these lambdas with a template head also enable much more code reduction. So it's a cool feature. And here is, just to increase your appetite, 2 more examples. So the first one at the top, I'm creating a lambda. It's a lambda with a template head. On the angle brackets, it has a type named t, and as a parameter, it now takes a std vector of t. So it's no more auto at this point. It's a std vector, but the t inside, that's variable. So now I can call this creating in line number 2 a state vector of int, and I can call my lambda with v, the vector. But I can no longer call it with just the number 20. That will not compile. It's not a std vector. Okay, so that's brilliant. And because I told you we can also use non-type template parameters, the example below that says it creates a lambda which in the template head takes a size tn. So let a compiler deduce the size. The size of what? The size of the std array in the parameter list of the lambda. Because this lambda takes a std array of int of n, and n is deduced by the compiler. So in line number 3, I'm creating such a std array, and I'm passing it to the lambda in line number 5, and that works. It would also work for a std array of int of 5, of 9, whatever you want, but it would not compile for a std array of, for example, char on 2. Okay. So lambdas with a template head enable us to do way more things with lambdas when it comes to generic contexts. And I really, really like that. All right. So far with that, I will answer the questions I'm seeing in the Q&A after I close the talk right now. And I will also take questions from, I guess, the live audience in the real venue. So I hope I increased your appetite for C++20. It has way more than just concepts, but I think concepts are a really good part and a really large part of C++20 that will influence our code and how we write code. If you like, you can subscribe to my newsletter and download a concepts cheat sheet. It's 2 pages of what I think the most important things of concepts are and how they are arranged with examples and figures and so forth. And as I said, you can also buy my Programming with C++20 book or attend my class at CppCon next Mondays or in a week. Before answering your questions, to close this official part, all that's left for me to say is, I am fertig, or in German, ich bin fertig. Remember the 2 times or the 2 different meanings for that. So thanks for attending. And now going to your questions. What do you see here? So the first question is, for concepts, why we are not verifying the return type of various operations, e.g. t.begin. It might exist, but not return an iterator and is unlikely to satisfy all the other requirements. But is there an easy way, is it recommended to verify this more strictly? That's a good question. As far as I know, we started introducing concepts in C++20, but we didn't change the entire standard, introducing concepts all over the place. The only feature where concepts are used currently in the standard, if I'm right, are ranges. So ranges are the first user of concepts. And I can imagine a world in the future where std.begin has these checks. The problematic part here is it's the question whether this is an API or an ABI change if we add a concept to an existing begin function in the standard library. So this might be a reason not to do it. But in your own code, feel free to apply concepts and make the implicit requirements really visible and touchable. Okay. So next question. You're saying requires in parentheses TT, so we are looking at a requires expression. If I repeat it like requires T comma const T CT, can I check for constant methods separately? So if I understand this right, you're asking whether you can check that the method that you're calling is const if you put const in front of the type you're passing to a requires expression. So in the parameter list of the requires expression. And I think the answer is yes. So if you make it const, then the const member function will be called. If it's non-const, then the non-const member function will be called. And that way you could ensure by using both parameter or both combination of parameters that you're having the const and non-const member function available on there for that. Yeah. So on slide 23, thanks for using the slide numbers. Does the compiler evaluate the expressions t.size, or is it just checking whether they are valid? This is a simple requirement we are looking at here. So it only checks whether this is valid, meaning is size available in the type, okay? It doesn't do anything more. For that, the method at least had to be const, expr, and things like that, which, yeah. But this is a simple requirement here. Okay, what's next? What implications do concepts have for polymorphism? This is a compile time mechanism for enforcing class data and behaviors, an effective replacement for CRTP. Yes, in fact, I can see a world where we may do less virtual things and use concepts more often. Okay, I think it depends a little bit on your environment and how good the compilers are to optimize all that stuff, because when we talk about templates or abbreviated function templates, for example, then we have a risk of creating more code or ending up with more code than we wanted. But yes, I can see that, especially in these places where we don't really need the inheritance, but just have to ensure that the type that gets passed in satisfies a dedicated or some interface, that can, in my opinion, in future be a concept and the generic function. It doesn't have to have the base class and override the member functions there and so forth, and we're paying with a vtable and all that stuff. I can totally see that, yes. So I think polymorphism can be reduced by concepts in places where it makes sense. So the next one is, what does this mean for libraries that have been previously written without concepts? Any advice for migrating libraries written using old template patterns for concepts? Well, the thing that I can tell you is you have to be careful. If your library wants or promised to provide a stable ABI, then it may be difficult changing the template parameters and flipping over to concepts, because that can be end up encoded in the names of the types, and then yeah, your customers may be unhappy. That's the one thing I can tell you where to watch out for. Other than that, I think you can approach me with a specific example. Maybe then I can give you more dedicated tip. But for the broad question, I don't have a tip that at least fits in the time we already overrun. So next question is, in the lambdas with template head section, do these lambda function need any definition in the .h file, or is everything defined ad hoc in the CPP file? As always, for lambdas, they are defined where they are defined. So you don't need a .h file and then distribute it. You can simply, the code I showed on the slide that can supposedly be directly in main.cpp, and they're in main, so no header required. It's where you define it. It's complete there. And saying that lambdas are the, where do we have them? That's the only way we currently have in the language to define a method template inside a function, okay, as a side note. Next question, would using concepts over polymorphism dramatically increase build times? Well, that's a tough question. First of all, the question is what's dramatically? I think it depends on your code base and how heavily you're using concepts. But in general, I can imagine that it increases build times. Concepts in general, if you do the comparison between checking an enable if or a concept, if you come up with a simple example and instantiate it often enough, then you will see that the enable if is just horrible for the compiler. So your concept version is way faster. Okay, that's one thing to take away here. Using concepts can increase your build times if you just switch from enable if to concepts. But as we had this before, if we flip from polymorphism to more generic code at this point, then yes, I can see that it will increase your build times because we have more generic code there. And that's creating more instantiations. So I guess to some extent, yes, it will increase build times, but compilers get better, our systems get better, so maybe we will no longer notice this at some point. So next question, and I think we have to shut this down slowly down, but I'm really happy about all your questions. As I said, feel free to approach me later on Discord. I'm happy to take questions there, but I will not be able to join the virtual venue today. So the next question is adding on to the Santi's question on slide 23. So does it mean the expression has to be well-formed? So you're saying slide number 23 was the one here. This expression there has to be well-formed, yes. You can compare it like you write it in real code. So if you omit the semicolon, then it will not compile. If you would say t arrow size and I'm passing in an object, it would not compile. So yes, it has to be a well-formed code at this point, yes. All right, next question. So no, something flipped. Because you upvoted that one. Okay, so you first used first argt for something. What? The question is gone. Where's the question?
Oh, I'm really sorry. I marked it as answered, so you can.
That's all right. I try to find it. So I think I have it. So you used first argt for something like that to get the type of the first argument. Where can I find a documentation for more functions like that? Well, I think the best place to learn this would be the type traits header. And other than that, I don't know. Sometimes doing a GitHub search for something reveals something. So maybe reach out to me if you have more specific things in mind, then I can point you to something. But sadly, there is no sole document which lists all these. Some blog posts sometimes go into details for what's interesting and maybe helpful at this point. So and then the last question I'm seeing here is copied from your comment. That's nice. For overloads, const R value, L value with different return types, does it mean we would have to manually cast it? Should move t begin to something you're saying. I see. You're in a compound requirement and you're asking whether you have to move L or R values. And you want to do this because, now I see, you want to do this because you want to check this specific overload of, in your example, the begin function of my type T. So yes, then casting is an option. Yeah, to check even more overloads. Perfect. Yeah, that makes sense. All right. With that, I think we have all currently open questions answered. Thank you very much for them. It was fun. As I said, feel free to grab me for the rest of the week. I'm available on Discord and sometimes at the virtual venue, and ask the questions that are still open. Okay. I hope you enjoyed the talk. And as I said, C++20, it will be great. May take a while until all compilers have the same level of support, but they're getting there. So looking forward to a bright future with C++20 and concepts. Have a nice day, and bye-bye.